On October 7, 2025, the European Space Agency released the first official image of 3I divided by Atlas, an interstellar object caught passing near Mars. The world expected a breakthrough. Instead, we got a faint, fuzzy dot and a 4-day silence from every other major space agency. Why would NASA, China, and the UAE hide their best images while ESA alone tried to explain away chemistry that shouldn't exist? A trajectory almost too perfect, and a coma nearly pure carbon dioxide. If 3I divided by Atlas was just another comet, why does every answer raise more questions? And what do 7 spacecraft know that we don't? This is the story behind the images that changed everything. On October 2, 2025, just after 9:00 inches the morning, local Mars time, the Perseverance rover's SkyCam snapped a picture that wasn't supposed to matter. SkyCam is a wide field color imager built for monitoring dust, clouds, and the Martian horizon, not for chasing interstellar objects. But while the world waited for high-resolution images from orbit, it was this humble camera that caught the first clear sign of 3I divided by Atlas near Mars. The official RAW frame later released by NASA showed a faint green circled speck against the washed-out Martian sky, a dot so subtle that most would have missed it if not for the annotation. The odds were stacked against any detection. Daylight on Mars is harsh, scattering sunlight through dust and making faint cosmic visitors almost invisible. SkyCam sensor optimized for landscape shots struggled to pull out anything beyond the brightest feature. Yet Mallory Lefland, the rover's shift lead, pushed to keep the camera running. She argued that even a marginal capture could prove historic, especially with the US government shutdown threatening to freeze all but essential operations. Her call paid off. The image time-stamped 0918. Mars local time became the first tangible evidence that 3-2 divided by Atlas had entered Mars's neighborhood. No other instrument on Mars was designed to watch the whole sky at once, especially in daylight. While orbiters and science cameras waited for the perfect alignment, SkyCam's wide view made it possible to catch the unexpected. The result wasn't pretty. A grainy patch barely distinguishable from noise, but it was there, undeniable. This single frame captured by a camera meant for weather anchored the entire chain of observations that followed. The search for answers now had a starting point. A real image taken from the surface of another planet, showing an interstellar object in Mars's sky. October 3, 2025 brought a rare alignment above Mars. 7 spacecraft, each with a different specialty, found themselves in position to observe 3-2 divided by Atlas as it passed just under 30 million kilometers from the planet. This was not a routine flyby. It was a convergence of sensors, each primed for a single chance at an interstellar visitor. HiRISE, the high-resolution camera aboard Mars Reconnaissance Orbiter, is built to capture Martian landscapes in detail, sharp enough to spot a rover's tracks. Its field of view, though, is narrow. Catching a moving comet at this distance meant threading a cosmic needle. KSSIS on the ExoMars Trace Gas Orbiter offered more flexibility. Its panchromatic imaging could stack exposures, trading sharpness for sensitivity to faint, drifting targets. Theus on Odyssey, tuned to infrared wavelengths, hoped for a thermal signature, but the odds were low. Most comets are invisible to its detectors unless actively venting gas or dust. Mars Express contributed 2 spectrometers, Omega and SPAN, both designed for mapping surface minerals and atmospheric gases. Their strength lay in dissecting the coma's chemistry, looking for telltale fingerprints of carbon dioxide, water, or something stranger. Nomad, a 3rd spectrometer on Trace Gas Orbiter, was tasked with teasing out the faintest traces of volatile compounds, potentially exposing the comet's interstellar origins. China's Tianwen orbiter added multispectral and radar eyes, unique in its ability to probe both composition and structure if the geometry cooperated. The UAE's HOPE probe circling higher above Mars brought ultraviolet and optical monitoring sensitive to broad changes in coma brightness and shape. Each instrument faced its own hurdles. brightness thousands of times below normal targets, tracking a point moving across the sky, and limited exposure time. Yet for a few hours, Mars became the best vantage point in the solar system. The full array of sensors, from high-res images to spectrometers, stood ready for a dataset that would be impossible to repeat. In this fleeting window, the promise was clear. If any anomaly or revelation was to be found, this was the moment the world's orbiters and probes would catch it. EA's public release arrived on October 7th. Instead of a sharp portrait, the world got a looping animation, a faint, fuzzy dot drifting across a black field, surrounded by a barely perceptible haze. This was the KSS camera at work on the ExoMar Trace Gas Orbiter, pointed at the predicted path of 3 divided by Atlas as it swept past Mars. The challenge was immense. According to Nick Thomas, the principal investigator for KSSIS, the comet was at least 10,000 times dimmer than the typical Martian targets his team tracked. To avoid distorting the signal, Thomas limited exposures to 5 seconds per frame, a conservative call that prioritized data integrity over dramatic visuals. The resulting GIF compresses hours of effort into a few seconds of motion, with each frame capturing a target on the edge of detectability. What the animation shows is not the comet's nucleus, which remains unresolved even at this distance, but its coma, a pale envelope of gas and dust stretching several thousand kilometers across. The coma's brightness fades rapidly, dissolving into the background noise before any tail becomes visible. Spectroscopic analysis, the key to deciphering composition, was flagged as uncertain in ESA's statement. The raw data, along with all Level 1 products, remains locked under the agency's standard 6-month embargo. Only this processed preview is public, a placeholder for deeper analysis still underway. Outreach norms demand something to show, but the reality is that most of what CASIS captured is still hidden from view. ESA's press office pushed for a more striking image, but Thomas stood firm. No artificial stretching, no overprocessed contrast. The risk of misinterpretation was too high, especially with rumors swirling about unusual chemistry and possible anomalies. For now, the only official glimpse is this subdued animation, a modest but vital record of an interstellar visitor at Mars. The scientific world is left waiting, knowing the real answers are buried in data that won't surface for months. On October 4th, 2025, mission leads from NASA, the European Space Agency, China's CNSA, and the United Arab Emirates gathered for a confidential teleconference. The call wasn't scheduled on any public calendar, and no transcript has surfaced, but its impact was immediate. For the next 3 days, every agency with eyes on Mars went silent. The only data released came from the European Space Agency, a single cautious animation and a written statement that sidestepped specifics. NASA cited the ongoing US government shutdown as a reason for limited updates, but that excuse didn't apply to European or Asian partners. China and the United Arab Emirates, both operating under different political pressures, offered no explanation at all. Inside the European Space Agency, the tension was clear. Communication staff wanted a dramatic reveal, something to match the public's expectation for a historic interstellar encounter. But risk officers and science leads pushed back, invoking language usually reserved for planetary defense events, anomalous preliminary data, potential for misinterpretation, and need for interagency review. The phrase media-driven speculation outweighing public trust appeared in more than one internal memo. In the days that followed, draft statements were edited and re-edited, with every mention of unusual chemistry or unexplained optical effects replaced by bland assurances of ongoing analysis. The silence wasn't just about what was shown, it was about what was withheld. The European Space Agency embargoed raw KSSIS data under standard 6-month rules, but even summary statistics on polarization and spectroscopy were trimmed to the bare minimum. NASA's Mars Reconnaissance Orbiter and Perseverance teams released nothing beyond the annotated SkyCam frame, redirecting all queries to headquarters. China's Tianwen-1 and the United Arab Emirates Hope probe both equipped to capture unique spectral and radar data, posted no updates, not even confirmation of attempted observations. The usual rhythm of science, raw files, quick looks, engineering logs, stopped cold. Space policy analysts notice the pattern. Competitive agencies rarely coordinate their silence, especially when a high-profile discovery is at stake. The last time anything like this happened was during asteroid flybys with planetary defense implications, when early data could trigger panic or confusion. But this was a comet, not a threat. So, what kind of anomaly could force four agencies with different priorities and rivalries to hold back everything but the safest preview? Some pointed to the risk of misreading faint signals or triggering wild speculation about artificial origins. Others suspected deeper disagreements over how to vet and interpret the first hints of non-standard chemistry or unexpected polarization. The coordinated quiet left the scientific community in limbo. Outreach teams fielded questions they couldn't answer. Amateur astronomers tried and failed to match the Skycam detection, fueling rumors that the real story was hidden in embargoed files. For now, the only certainty was that something in the preliminary data, whether a calibration error, a physical anomaly, or simply the fear of a media firestorm, had convinced the world's top space agencies to wait. The expectation of open science had collided with a wall of caution, and behind it, the data waited for a verdict. Probability was never on 3 divided by Atlas's side. The object's path, just 5 off the ecliptic, threading between Mars in October and Jupiter's orbit in March, defied the odds. ESA's Space Situational Awareness Office ran the numbers. The chance of a random interstellar object following this geometry is less than 1 inch 10,000. The trajectory alone raised eyebrows, especially with the flyby sky patch brushing so close to the coordinates of the 1977 WOW signal. Official memos dismissed the overlap as coincidence, but the statistical unlikelihood fueled debate among mission scientists. Spectroscopists found themselves staring at an even stranger puzzle. Early spectra cross-cheed between VLT and JWST showed strong atomic nickel lines Ni without a trace of iron. In comets, nickel and iron usually travel together, liberated from grains by heat or ultraviolet light. Here, iron was missing, even as nickel production rates soared with each approach to the Sunday. On August 21st, the VLT logged a nickel production rate near 10 to the power of 22.7 atoms, divided by S, with a scaling law, so steep falling off with heliocentric distance to the ETH power that it outpaced any known cometry behavior. Laboratory analogies point to one pathway: nickel carbonyl, a volatile compound that forms in carbon monoxide-rich environments and breaks down under mild heat or sunlight, releasing pure nickel atoms. On Earth, it's an industrial process. In space, it's almost unheard of. The absence of iron carbonyl signatures and the lack of any FEI emission left the chemistry team at DLR and INAF searching for natural explanations that fit the numbers. The coma itself, sampled by JWST in the near-infrared, told a second story. Carbon dioxide made up 95% of the detected gases, an extreme, almost unheard-of ratio. Water, the staple of most comets, was barely present. Some theorized that long interstellar exposure could drive off water ice, leaving heavier volatiles behind. Others wondered if the ratio hinted at something more deliberate, artificial outgassing, or propellant use, though no direct evidence supported that leap. For now, the CO2-rich coma stood as a chemical fingerprint, rare but not impossible in nature. Optical measurements added a final twist. KSSIS and VLTS-FORS-2 both recorded extreme negative polarization, -4 or more at red wavelengths, far beyond the usual range for comet dust. Negative polarization means the coma's dust grains scatter light in a way that strongly favors backscattering, often linked to fine carbon-rich particles or metallic clusters. In solar system comets, values rarely dip below -2. Here, the readings were almost double that, consistent across multiple instruments and phase angles, no calibration error could explain the effect. The numbers held up against standard stars and repeated run. Taken together, the evidence painted a picture that was anything but ordinary. A hyperbolic path with uncanny planetary alignments, a chemistry set dominated by nickel and carbon dioxide, and optical properties that pushed known physical models to their limits. Each anomaly on its own could be written off as a statistical fluke or a rare natural variant. But as the data stacked up, the search for a single conventional explanation grew harder to defend. The files sitting in embargo, raw spectra, Stokes parameters, and engineering logs became the focus of a scientific riddle that demanded more than routine answers. For now, every hypothesis would have to account for these outliers: the trajectory, the chemistry, and the light itself. Scientists faced a puzzle that demanded a framework: 4 competing models, each with a different path to the truth. The first and most conservative treats 3-2 divided by Atlas as a natural comet with exotic chemistry. If that's right, future spectra should show the same nickel dominance and carbon dioxide-rich gas, but also reveal hidden iron or water lines as the coma evolves. The second hypothesis considers the object an ancient artifact, a probe or observer, perhaps long dormant. This idea fits the industrial-like nickel chemistry, but so far there's no evidence of structure or artificial signals. Only high-resolution radar or unexpected tumbling could tip the scales. The third model proposes an active reconnaissance platform, optimizing its trajectory for planetary flybys. Its path fits, but there's no sign of telemetry, outgassing maneuvers, or energy output. Detecting a sudden change in speed or brightness after perihelion would be the key test. The last, most speculative, a hybrid craft, hiding an engineered core inside a natural shell. This would explain the natural exterior and the anomalous chemistry. But again, no direct evidence of non-tri behavior has surfaced. Only post-perihelion deviation or fragments with unnatural motion could confirm it. Each theory stands or falls on data yet to come. And for now, the tests are clear, even if the answers are not. October 29th, 2025. As 3 divided by Atlas swings closest to the Sun, the entire inner solar system loses its view. From Earth and Mars, the object disappears behind the solar disk, blocked by a wall of plasma and glare that no optical or radio instrument can penetrate. For 2 weeks, the region around perihelion is a blind spot, erasing the most critical phase from every telescope and probe. This blackout is more than a technical inconvenience. It's a natural cloak at the moment of maximum activity when comets are most likely to brighten, fragment, or if the object is not entirely natural, execute a maneuver. Mission planners have no choice but to wait, knowing that any sudden change in trajectory or the appearance of new fragments will go unrecorded. The checklist for reemergence is clear: track the path, search for deviations, measure the coma's brightness, and scan for unexpected companion. What happens in the glare may decide which theory survives. But for now, the data stream goes silent, and every answer must wait for the comet's return to the night sky. Late November brings the first new opportunity to catch 3 ice divided by Atlas after its disappearance behind the Sunday. ESA's JUICE spacecraft, now outbound from Jupiter, will point its high-resolution Janus camera and MAGIS spectro-imager toward the predicted path. The geometry is tight, just under a degree from Jupiter in the sky, but the probe is well positioned to capture the coma if the object remains bright enough. JUICE's data won't arrive instantly. Even preview images face a 3-day lag, and full science products may take up to 2 weeks to clear calibration and quality checks before reaching the Planetary Science Archive. Juno, looping in its extended polar orbit, will get its shot in mid-March 2026. On March 16th, the spacecraft's alignment allows JunoCam to scan for outgassing jets or fragments that might betray non-gravitational forces at work. The window is narrow, and the data pipeline is slow. Images could take a month or more to reach public release. Both teams are preparing contingency plans in case 3i divided by Atlas veers off course, or dims unexpectedly. For now, the world waits as these distant sentinels ready their sensors, hoping to catch the next act in a story that has already rewritten the rules of cosmic observation. Despite 7 spacecraft being aligned for observation and Perseverance's earlier Skycam capture, NASA, China, and the UAE have not released their images or findings. The coordinated silence, which an internal agency call on October 4th acknowledged, is unusual for international science campaigns. Available data reveal a trajectory with less than 0.01 carbon dioxide. Unlike any known comet, experts agree that the true nature of 3.2 divided by Atlas remains unconfirmed, with key tests delayed until after the October 29th perihelion blackout. As ESA and other agencies prepare new releases and JUICE plans late November observations, one fact stands. The most significant interstellar flyby since Oumuamua has raised more questions than answers. And the next images may reshape what we know about visitors from beyond our solar system.